Section 4 we'll be working to solve trigonometric equations. And if you remember, because trigonometric equations, right, they go on and on. If I graph them, they go on and on and on. And if we look at a specific solution like this, you'll notice that I have lots of solutions. I have a solution here and here and here and here and here and here for a value of y is equal to some value, right? So when we work with solving these functions, we're going to express them in a way that's maybe a little different than what you're used to. And of course, we have the return of the idea of extraneous solutions. Those are, of course, solutions that we've solved for algebraically, but don't actually work in our equation. So one type of equation or problem we might solve using some of these skills is the idea of the water depth D for the Bay of Fundy has this modeling. Now the Bay of Fundy is known around the world because it has a really extreme high and low tide. So this is what it looks like at high tide, and you see at low tide all of this has been exposed. So it's got very extreme tides. And then of course tides follow that sort of function like a sine or a cosine curve because they go down and they come back up again, and they go down and they come back up again. Okay, so this is the type of problem that we might take a look at. But let's practice something simpler first. So at this point, find the general solution of the equation. So I want to solve for the sine of x. So if I add 1 to either side of the equation and then divide by 2, I want to find the sine of x is equal to 1/2. So if I take and I graph y is equal to the sine of x, I can start into this process. So if I go ahead and go through the process we've already learned I'm going to solve by graphing because I think it's easier to show you. And in this case, I know that A is equal to 1 and B is equal to 1. So I know that my amplitude is 1. I don't have an h or k in this, so there's no shifting here. So I know that I'm going to go between 0, 1, and -1. B is equal to 1 as well, so my period will be 2 pi over 1, which is 2 pi. And if I just take a look at one cycle, I'm just going to examine one cycle for now. Pi over 2, and 3 pi over 2. And we want to find where 1/2 exists. If I just graph this, I know that I start at 0, and then I go to the upper amplitude, back to the midpoint, lower amplitude, and this is what my graph kind of looks like. And what I'm looking for is I'm looking for here, right? 1/2 at 1/2. I would have solutions here and here. And then as my graph continues on into the future, you know that I'll also have a solution here and here. Well, how far are these items apart? Well, they're corresponding locations on different cycles, but so they're one period apart. So there's 2 pi between those. And if I look between this point and this point, there's 2 pi between there and there as well. So when I identify that value, it's not the only one. Then it's also going to be every distance 2 pi down the road, I'm going to come back to that same value. Well, thinking back to the unit circle, where does sine equal 1/2? And we go back to the unit circle. Sine is again related to the y values, right? Y values. So I'd have where y was 1/2 would be right here that's pi over 6, or 30 degrees. So if I want to express this, I'm also going to look over here because this is the other spot where y is 1/2. And this is 30 degrees, right? This is 30 degrees up from here, or pi over 6 up from here. This is pi over 6 back from pi. So sine is 1/2 at both pi over 6 and at 5 pi over 6. So if I want to, if this is pi over 6, and this is 5 pi over 6, then I know that my general solution is pi over 6 plus or minus n times 2 pi, meaning any number of sets of 2 pi. And I also have a solution at 5 pi over 6 plus and minus n times 2 pi. Okay, so the general equation general solution means everything, all the solutions, right? And in this case, I know that these are one cycle apart from each other. And likely you're going to find that's the way it's going to work regardless of how you find your solutions. Okay, so you're going to find two solutions. In this case, I found this solution and I found that solution. And then I had to account for the fact that those solutions occur every cycle by adding plus and minus, adding and subtracting the cycle, the full cycle length to this, or the period, plus and minus to each of my solutions. That allows me to get the general solution. So go ahead and take a look at trying that out. Do problems 10 and 11. And then come back and we'll talk about finding the solutions in an interval. So in this case, I now am only worried about this interval between 0 and 2 pi. So I'm going to go back and do something similar to what I did before, the 5 and the minus 7. This is going to be 2 times the sine of x minus 2 is equal to 0. If I add 2 to either side, 2 times the sine of x is equal to 2. And I divide by 2, sine of x is equal to 1. Then if I look at graphing this, right, you'll notice that we've got the same sort of scenarios that we've had in the past where a and b are equal to 1. These are very simple to work with. So I know my amplitude is 1. I know that my period is 2 pi divided by 1. Pi over here I'm going to be at pi over 2, and over here I'm at 3 pi over 2, and you'll find that these come up a lot in these problems. If I were to graph this, I'd be here, 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 and here. And this is a little different. You notice that 1, unlike when my solutions were here and here, because my solution is an extreme, it only happens one time in this interval. And in this case, it happened where? It happened at pi over 2. Okay? So x is equal to pi over 2. Now, you know, it might have occurred in two places. If it was 1/2, like it was in the last problem, it would have occurred here and here. And that would have been pi over 6 and 5 pi over 6. It could occur down here and here. It could have been -1, in which case it would have been just this point. But you'll notice when it occurs at the amplitude, rather than having pairs, you only have a single solution. So you just need to work with the problem and see what happens. Give that a try. Do problems 17 and 18, and then we'll work on something new. So again, now I'm working in an interval, but now I've got this more complex problem. And you see I have sine squared x, and I have sine to the first power x, and then I have a constant. And okay, so this is looking a lot like a quadratic function, right? So I'd want to see, are there factors of 3 that have a difference of 5? No, that doesn't really occur. So maybe I'm going to use the quadratic equation, right? In this case, I know that a is equal to 1, b is equal to 5, c is equal to -3. So this is a trigonometric equation, but it's in the form of a quadratic equation. I'm going to use the quadratic formula to solve it. Okay, so I know that I could do the opposite of b plus and minus -5 squared minus 4 times a times c. It's all over 2 times a. But what is this going to be equal to? It's going to be equal to the sine of x. Right? So it's not x, it's the sine of x. Okay, and if I go through and find sine of x is equal to, I'll have -5, plus and minus, I'll have 25 plus 12, that's going to be, 37. Root 37 over 2. So I'm going to have to come up with a function here, right? Where I'm going to need to pull out my calculator now and come up with a decimal for this. So let's go ahead and do that. So I'm going to have 37. The square root of 37 is 6. Let's put minus 5 and divided by 2. So 0.54138. And then, right, if that's the sine of theta, if I want to find theta or my value x, I'm going to have to do the inverse sine of that, and I'll get 32.77 degrees. So let's go ahead and write that down. Right, of this thing. So I get 32.77 degrees. And if I go back and I do that again, so I'll again take the square root of 37, I'll have the opposite of that, and I subtract 5, and I divide it by 2, I get that. Oh. So I can't find the sign of the negative number, so that's not going to work out. So if I have my 32.77 degrees, if I want to find it, oh, I'd have to convert that to radians, right? 32.77 times pi over 180. Right? And you know this is going to occur in more than one place, right? Potentially. But if we think about that, negative pi over 2 is here. Pi over 2 is up there. And we're talking about sine. All right, well, it's only going to be up here. Because these won't have the same sine value. They'd be opposites of each other. So if I have 32.77 divided by 180, that'll tell you how many radians it is. Okay, so that's how you would use that particular function to work this type of a problem out. Let me go ahead and do that. I'll have 32.77 divided by 180. And I'm getting basically 1 over pi over 16.3859. That's kind of a pain. Right, so I have pi over 16 point, let's call that 4. That's the angle that I get. Okay, so the point is when you're in quadratic form, then you can go ahead and solve. In this case, only one of my solutions was valid. Right? One solution came up as not a number, so the negative one was extraneous. I found a positive number and a negative number. The negative was extraneous. I took this guy, figured out there could only be one possible solution. The matching one would be over here, which is not in the interval they gave me. Okay, if I have another problem like this, 2 times the sine squared x of theta. Oh, so now this is just complicated, right? So what's sine squared theta equal to? Well, sine squared theta is equal to cosine squared theta and something else. Right? If you remember the trig identity, I know that sine squared x plus cosine squared x is equal to 1. that means that sine squared x is equal to 1 minus cosine squared x. So I can substitute this in place of that, and then I'll have all cosines. So I'll have 2 times 1 minus cosine squared x minus cosine of x minus 1 is equal to 0. So this would be 2 minus 2 cosine squared x minus cosine x minus 1 is equal to 0. I'm going to move everything to the other side. So it's going to be 0 over here because I want a positive leading coefficient, cosine squared x. I'm going to add cosine x to either side. And I had 2 minus 1, that's 1, and when I subtract it to either side, I get that. I want to see maybe if I could probably factor this. That looks pretty possible. If I have 2 cosine x minus 1 times cosine x plus 1, I'll have positive 2 cosine x minus 1 cosine x, that'll give me the positive 1, equal to 0. So I could have cosine of x is equal to negative 1 by setting this to be equal to 0, or by setting this to be equal to 0, cosine x equals 1/2. All right, we're in this interval, which is a big interval, right? That's the whole way around the circle. So where is cosine equal to negative 1? Remember, cosine is x. So where is x negative 1? It's over here on the unit circle. So at x is equal to pi, that would be one solution. And where is cosine 1/2? In that case, the x values are over here. When x is 1/2, I would be at pi over 3, and I would also be at negative pi over 3. So that would be pi over 3, which is 60 degrees. And then if I take pi over 3 negative, so I take pi over 3 out of 2 pi. 2 pi is 6 pi over 3, so it'd be 5 pi over 3. And these are my solutions. Okay, so that was sort of long and complicated. But you get the idea of working with a quadratically oriented function. I was able to factor it. I was also able to use the quadratic formula. So a bunch of different things worked out in this particular case. So in taking a look at this problem, I know that we're looking for the time when the depth is 7 feet. So 7 goes in for D. Terrible handwriting. Right, and the first thing I'm going to want to do is subtract 35. So I'll get negative 28 is equal to negative 28 times cosine of pi divided by 6.2 times t. Then when I divide both sides by negative 28, I'll get 1 is equal to cosine pi over 6.2 t. Now what's awkward at this moment is this cosine. So then my question is, when is cosine of an angle equal to 1? That's what I have. I have cosine of this angle is equal to 1. So what does this angle have to equal? Well, the only time that cosine of an angle is equal to 1, right, when my x-coordinate is 1, is right here at 0 degrees, but also as 2 pi degrees. And it would be 2 pi times any number of circles around the circle, 2 pi times n. So I know then that this angle has to be equal to 2 pi n. So if I set 2 pi n is equal to pi over 6.2 times t, that gets rid of the cosine. Now I multiply both sides by the inverse, 6.2 over pi times 2 pi n will be equal to time. So now I've solved for time. Right, the pi cancels with the pi. 2 times 6.2 is 12.4. N is equal to t. So what values of n could I use if I'm going to stay in the time period, right? So, and we're talking about a day, so my time has to be between 0 and 24, right? If we're measuring in hours. Okay, so what values of n could I possibly use for this? I could use n could be equal to 0, n could be equal to 1, but n can't be equal to 2 or anything more than 2. Okay, so if we look at that when n is 0, time is 0, so that's midnight, one of my solutions. And when n is 1, I'll have 12.4 times 1 is equal to t. So that's 12 hours. And then I have to convert 0.4 into minutes. Well, 0.4 times 60 minutes is 24 minutes, 12:24 p.m. All right, and there we go, midnight and 12:24 p.m. So the tricky part of this is realizing at this point that if cosine of this angle is equal to 1, then the angle has to be equal to 2 pi times whatever number of revolutions we've gone around the circle. Okay, and that's how you would go ahead and use this information to solve this type of a problem.